Now we will go to the second lecture of week 5 of this course, and in this lecture I will continue the discussion on crystal systems, okay, and unit cells. So, week 5 lecture 2 will be crystal systems and unit cells. Okay. So, in the last lecture we saw the crystal system classification that was based on symmetry, and again we emphasize that this is what we call the essential symmetry. Okay. And we said that a triclinic system there is no essential symmetry, and we had different systems. A monoclinic had a two-fold axis or mirror plane, a trigonal had a three-fold axis, hexagonal is 6-fold axis, orthorhombic had either 3 mirror planes or 3 two-fold axis, tetragonal had 1 4-fold axis, and cubic had 4 3-fold axis. Okay, so these were the essential symmetries for various systems. Okay, and now what we will see is we will look at these symmetries in the context of what we have seen before, which is the shapes of the unit cells. Okay. And what we want to see is that we want to look at the unit cell of the crystal, okay, and its shape in terms of these symmetries. Okay. Now, just to remind us, okay, so we said that each unit cell has a shape, and the general shape is represented as a parallelepiped, okay, and this parallelepiped is made of 3 different ABC, 3 different vectors which have 3 different angles, and let me show this B slightly differently, BC, and you can make a parallelepiped using these three segments, and you can generate the unit cell. So we said that we showed that this is a very convenient way to look at unit cells in terms of ABC, and there are different angles that we defined. So the angle between B and C, okay, so call this B, and C we called it as alpha. Between A and B, okay, so this between A and B we called it as gamma, and between A and C we called it as beta. Okay, so we had these 3 angles, alpha, beta, gamma, and these 3 cell parameters A, B, C. A, B, C are 3 lengths. Okay, so these 3 lengths and 3 angles can be used to specify the shape of the unit cell. Okay. Now, what we said is that for different crystal systems you have different unit cells, okay, and these unit cells are specified by restrictions on the parameters. Okay. And again what is important is that these are unit cells of crystals, okay, and these just contain these parameters A, B, C, alpha, beta, gamma. So it just tells you in some sense it tells you what are these parameters of this repeating unit. Okay. Now, what we earlier saw is that your crystal is a lattice plus basis, and we also saw that these unit cells, okay, they also can be related to Bravais lattices. Okay, for example, we know that some cells, some unit cells can have primitive face centered, body centered, or edge centered, and so on. Okay, so they are related to Bravais lattice, and we also saw that the overall crystal is consists of a Bravais lattice and a basis or a motif. Okay, and this if you have an unsymmetrical motif, then there can be a reduction in symmetry. Okay, so the symmetry can be reduced because of presence of an unsymmetrical motif. Okay, so for example, if you have a cubic unit cell, you have a unit cell that is cubic, that is shaped like a cube. So in other words, A equal to B equal to C, alpha equal to beta equal to gamma. Okay. Now suppose I put some unsymmetrical unit. Okay. So let me put something that looks like this object. Okay. And let me take just a primitive cubic. So the lattice is definitely a primitive cubic lattice, but I have this unsymmetrical motif. Okay. So I can write this as primitive cubic lattice plus this motif. Unsymmetrical motif. Okay. Now you can see that this threefold axis is not there. So we can see that because of this unsymmetrical motif, okay, you rotate it by 120 degrees. Okay, then you can clearly see that these two will not go on top of each other. Okay. So the threefold axis, okay, is not, so this is not a threefold axis anymore. Okay, so even though the unit cell is cubic, looks like a cube, okay, because of this unsymmetrical motif, it is not a cubic system. Okay, so this is not a cubic system. So it does not belong to a cubic system, and this is very important, that the symmetry of the crystal is very different from the symmetry of the unit cell. So the unit cell is a simple cube, okay, but the symmetry of the crystal is very different from that of the unit cell. Okay. And so given this, we think now, however, you can also think that suppose you had a cubic system, and then the unit cell would definitely satisfy A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees. Okay. So cubic system automatically implies A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, but not the other way around. Okay. So let me write it this way. So cubic system implies, okay, that must mean that unit cell satisfies A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees. Okay. However, this is not sufficient. However, just because a unit cell satisfies this, okay, just because a unit cell satisfies A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees, this does not imply a cubic system. Okay. So you could have the same unit cell shape, but a very different system. All right. Okay. So that is to be kept in mind. Now let's look back at these restrictions, and again what is very important is that you look at these as restrictions. Okay. So, restrictions, okay, and what is important while you write these restrictions is to keep in mind that the phrase not equal to means need not be equal to. Be equal to. Okay. So, it need not be, it can be equal, but it need not be equal. Okay. So, so as we said, in the triclinic system there is no restriction on ABC. Okay. So, so it is often written as A is not equal to B, not equal to C, but actually what it means is it need not be equal to C, B it need not be equal to C, and alpha need not be equal to beta, need not be equal to gamma. Okay. So, so keep in mind that it is not that A, B, C have to be different, they could be the same and still it could be triclinic. Okay. They could be the same and it could still be triclinic. Okay. But to be a triclinic system they need not be equal, and if they are equal it is fine, you can still be a triclinic system even with A, B, C being the same. Okay. What is important is the symmetry of the system. So, for triclinic what is important is that they should satisfy this essential symmetry of 4 of, and the essential symmetry is basically none, no essential symmetry. For a monoclinic, so for a monoclinic, okay, now again A need not be equal to B, it need not be equal to C. Okay. However, you should have alpha equal to gamma equal to 90 degrees. Okay. So actually the restriction is only this is the restriction, this is the only restriction. Okay. And what we will say is that beta need not be 90 degrees. So, beta need not be 90 degrees. Okay. So, the only restriction is that alpha should be equal to gamma equal to 90 degrees. Now, what is the essential symmetry of a monoclinic? Okay. So, it should have one two-fold axis or mirror plane, 1, 2 or mirror plane. Okay. So, if it has 1, 2 or a mirror plane, then it can be a monoclinic, system. Okay. Again it could have more and it could be some other system also, but if it has 1, 2 or m it can be a monoclinic system. Okay. So, that is essential. Without this you cannot have a monoclinic system, without a 2 or a mirror you cannot have a monoclinic system. Okay. Now, the trigonal, there are two trigonals, there is trigonal A where in which case you have A equal to B and it need not be equal to C, and you have alpha equal to beta equal to 90 degrees and gamma equal to 120 degrees. Okay. So this is like one third of a hexagonal cell. Okay. And the symmetry is, the essential symmetry is 1 3 axis. So, it should have a, if it has a 3 axis then you can call it a trigonal system. Okay. Now, trigonal B is also in the same class. So, that will also have only one 3 axis. Okay. And again let me circle the restriction. So, the restriction says that A has to be equal to B and alpha has to be equal to beta equal to 90 degrees. Okay. So, clearly in a cubic system A is equal to B and alpha equal to beta equal to 90 degrees. Okay. So, a cubic system can also be a trigonal system. Okay. So, that is to be kept in mind. Okay. Now, the trigonal B is in terms of unit cells it is slightly different. Okay. And this is the R centered trigonal system. Okay. Here you have A has to be equal to B and it has to be equal to C, and alpha, beta, gamma are equal to each other, equal to gamma, and they need not be 90 degrees. Okay, so they need not be 90 degrees. Okay, and this also has only one 3-fold axis. So the restriction on the unit cell parameters is that A, B, C should be the same, alpha, beta, gamma should be the same. That is the restriction on the unit cell parameters. Okay, and the essential symmetry is that it should have one 3-fold axis. Okay, what about the hexagonal? Hexagonal, in the hexagonal system, again you have exactly the same unit cell shape as the trigonal A. So A equal to B and need not be equal to C, and alpha equal to beta equal to 90 degrees, and I should emphasize that this is also a restriction, and gamma equal to 120 degrees, that is also a restriction. Okay, so all these are restrictions. But the essential symmetry for a hexagonal system is one 6-fold axis. So it should have a 6-fold axis. Okay. Now for the orthorhombic system, okay, the orthorhombic system, we said A is not equal, A need not be equal to B, it need not be equal to C. However, your alpha has to be equal to beta, has to be equal to gamma, equal to 90 degrees. Okay. So the restriction is that alpha, beta and gamma should all be 90 degrees. Okay. And this has an essential symmetry. Okay. So because alpha, beta, gamma are all 90 degrees, okay, the essential symmetry here is 3. So it should have not 1, but it should have 3 2 axis or M. Okay, so 3 2-fold axis or 3 mirror planes. Okay, so if a system has, if a crystal has 3 2-fold axis or 3 mirrors, okay, then it falls in the orthorhombic crystal system. It can be an orthorhombic crystal. Okay, notice that monoclinic, the essential requirement is 1, 2 or M. Okay, so an orthorhombic system can also be monoclinic. Okay, it can be monoclinic. Okay, and but this is the essential symmetry to be orthorhombic. Okay, and then what about a tetragonal system? Tetragonal system, we said that A is equal to B and it need not be equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. Okay. Again, the essential requirement of tetragonal is that all the 3 angles should be 90 degrees. Okay. Now in this case you will have 4-fold axis. Okay. So you will have one 4-fold axis, and finally for a cubic system we have A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. So this is a restriction on the shape of the unit cell. Okay, so a cubic system should have this shape of the unit cell. Okay, and again let me emphasize that just because you have this shape, it need not be cubic, it can be many other things. Okay, and it should have 4 3-fold axis. Okay, that is the essential symmetry. Okay, so this is a way to understand how the restrictions on the unit cell shape, okay, arise for different systems. Okay. Now again what is important is that these are only the restrictions are important. Okay. The not equal to sign that you see in all these relations, okay, that means it need not be equal to, it can be or it may not be. Okay. But what you know is that for a cubic system the unit cell has to satisfy A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, but not I mean, it does not imply that every unit cell that has A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees is a corresponds to a cubic crystal. Okay. So, I will conclude this lecture here, okay, and we will now look more closely at the different point groups and space groups in the next class. Thank you.